Hello everyone, my name is Ben Wells. I am a rising senior at San Diego State University where I study environmental science with a minor in engineering. And today we're going to be looking at black carbon and how it changes both spatially and temporally over the LA Basin. So, what is black carbon? When I was first coming to grips with it, I thought of it as this black smoke product that comes out of these diesel trucks when you're driving down the I-5. But another name for it is soot. So how it's produced through incomplete combustion. So basically what that means is something isn't burned all the way through and produces a particle. Those particles have a pretty short lifetime in the atmosphere, which is good for us and our lungs. And the source of these black carbon particles can come from everything from burning of fossil fuels and fires. We're going to see a lot of fires. And those burning of fossil fuels can come from the form of coal-fired power plants, automobiles, or even agriculture. So why do we care about black carbon? Well, we care about black carbon. You see this black color coming from this oil refinery right here. That black color absorbs that radiation from the sun and keeps that heat in our atmosphere, acting almost like a greenhouse gas. Also, a lot of the black carbon that we see in our glaciers comes from North America and Eurasia. So I think of this as almost like instead of wearing a white shirt on a sunny day, you're now wearing a black shirt and you're absorbing all that heat. So now our glaciers are absorbing that heat rather than reflecting it back with the albedo effect and melting at a quicker rate. Also the human health effects, I say similar to PM 2.5 just because the size of black carbon is smaller than 2.5 micrometers. And the health effects that we see with PM 2.5 tend to be cardiovascular disease, cancer, premature mortality, and asthma. And it works by basically it's so small that it's able to get deep down into your lungs and cause human health effects like we see. So how do we get this black carbon? How did I get this data? Well, we used the SP2. So we did an SP2 on our 2024 SARP flights on the P3B. Basically what the SP2 is, it's a single particle soot photometer. How it works, it's a laser-induced incandescence instrument. So when I first saw that, I was like, what does that mean? That's not English. So basically how it works is there's an inlet on the plane, and a little tiny particle of soot is going to come through that. That laser is going to light it up and basically produce incandescence. Incandescence is a fancy word for how much light. Our SP2 is going to basically measure that light and give us our black carbon mass. So that's how we're getting this data for the rest of the project that you're going to see. So when I was beginning this project, I knew I wanted to compare data between different years. So I did 2016 and 2024 SARP. But what I also found was a study by Calnex in 2010 where they flew over a similar area. So you can see how they fly over the LA Basin and also the Central Valley, which is similar to us. For us, we are just going to focus on the LA Basin. And there, as I said, theirs is in 2010. They saw a maximum, so throughout the project, we are just going to focus on our maximum. We're not going to worry about our minimum. Our maximum, they saw 530 nanograms per cubic meter, and their average was about 172 nanograms per cubic meter, which we'll compare later. So this is our flight path over the LA Basin. The purple that you're going to see is where there's areas of high black carbon. I used 400 as my sort of cap for the colors, just based off what Calnex did. And then anything over 400 is where we're going to see these blacks. So this is most likely going to be our hotspots, especially in the LA Basin. And then our next flight, we also flew over the LA Basin on July 1st. These are all on the P3B. Same thing. Purple and the dark blue is going to be where we see high levels of black carbon. That black is where we see areas super high. So we see it in East LA, we see it in Ontario. Central Valley is a little different. So Central Valley, we did a longer flight. That was on July 2nd, also on the P3B. Same thing, purple is going to be our darker ones. Where we see this purple over here is where we're going to see our hot spots, given that there's just so much less black carbon in the Central Valley. Now, we're also going to use 2016 data. So 2016 data, you can see the similar flight path. These are all created using ArcGIS. Basically, you can see that they spent a little bit of time over Los Angeles, a little bit of time over Long Beach, and then they did the Salton Sea as well, but not as much time as we did. Central Valley, very similar flight path to what we did. They did like maybe one more lap throughout the center of the Central Valley, but it's perfect for us because now we're able to compare that data. So with all this data, what did I want to do? So what I did is I structured it as how does the distribution of black carbon differ across California in different times. So we're looking at 2010, 2016, and 2024, how it's changing, where are those hotspots changing, and then what might be causing these hotspots observed from individual years. So what's going on? Why is it changing? So how we did this, first we did a data analysis. So I wanted to find out where this black carbon lives in the atmosphere. So basically, I created a vertical profile, average every 500 feet, and we're going to see where it is. Next, we identified outliers using statistical analysis for each flight. Basically, we created outliers for each one, because it's not fair to compare the Central Valley to the LA Basin. You have so much more black carbon that is in the LA Basin rather than the Central Valley, that if we held, for example, the Central Valley to the same standards that I held the LA Basin, we would see no outliers and be a pretty boring presentation. Now we're looking at our hotspots, what's going on. So we're going to investigate these hotspots, so we're going to look at things like carbon monoxide, we're going to look at things like ammonia, we're going to try and see, is it agriculture, is it transportation, is it fires, stuff like that. So let's get started. We're looking at a vertical profile over LA Basin here. We can see how we see most of our black carbon between 1,500 and 2,000 feet. What I would like to clarify is that this drop off right here is not necessarily saying what's actually happening. So the black carbon is emitted at ground level, and it doesn't just magically get to 1,500 to 2,000 feet. We don't have as many measurements on the P3B at 0 to 500 feet, just given that people would probably freak out if they're flying at 300 feet over the LA Basin. But you have less values right here, so we can assume that most of the black carbon is living between 0 to 2,000 feet. Now this is sort of a comparative graph. So we're looking at LA Basin, Salton Sea, and Central Valley. Again, Salton Sea doesn't just magically get to 1,500 feet. We don't have as much data from 0 to 500 feet. But what I want you to get from this slide is just the comparative analysis, so you can see how much difference in black carbon the LA Basin is than the Central Valley. Now we're just a straight up comparison table. So we're looking at 2010, 2016, and 2024. We're looking at our black carbon average and our maximum for each one. So in 2010, we see an average of 172 that CalMex reported, and then 184 nanograms per cubic meter in 2016, and then 233 nanograms per cubic meter in 2024. So we see a slight average, but there was some fires. There's not anything that would really grab our attention with this. Maximum, on the other hand, 2010 we see a maximum of 530 nanograms per cubic meter, and in 2016 we see a maximum of 4,318, so a giant increase. And then by 2024 we're seeing numbers of a maximum of 7,837 nanograms per cubic meter. So where are these hotspots in our LA Basin? So in 2016 we were seeing hotspots in Long Beach, we see East LA, and we see a little bit of Palmdale. Now in 2024, the trend that I want you to get from this is that it's slowly starting to move a little bit east. So we see our East LA, and we would probably see a little bit more of Long Beach if we spent more time there on the P3B. But what we start to see is this sort of move east, the San Bernardino Valley. You see Grand Terrace and Colton. Colton's about right here. There's a valley right there, and I was seeing high levels of black carbon right in that area. Now we're looking at the Central Valley. Central Valley stays relatively the same from 2016 to 2024. So 2016, we see it mostly located in the center of the Central Valley, and then also in 2024, the center of the Central Valley, with a couple differences. You see Bakersfield, but mostly the same. So now we're at the final part of the data analysis. What are we looking at? What's causing these hotspots? So when I'm looking at carbon monoxide versus carbon dioxide, what I'm looking for basically is fires. So I'm looking to see if we have high carbon monoxide and our CO2 isn't going up accordingly, that's telling me there's a fire. So what we would expect to see is we would expect to see something like Long Beach. So Long Beach, as our carbon dioxide goes up, our carbon monoxide really isn't increasing that much, which is good for us. It's the reason we have carbon monoxide alarms in our house. But this screams to me fire. And sure enough, in 2016, the Sherpa fires in Santa Barbara most likely bring in a lot of this carbon monoxide into our LA Basin, which people are breathing. Now we have total particles versus our carbon dioxide. So again, what we're going to expect is Long Beach. As our carbon dioxide is going up, our total particles are going to go up, given that it's just more human activity. What's interesting, and when I first made this graph, I was like, all right, Visalia we see in the Central Valley. Obviously, we don't see much particles or particle increase. Sorry, we do see more particle increase with not much CO2 increase. So what this screamed to me, since Visalia is in the Central Valley, I was like, we're going to see a ton of ammonium on the next slide. Like, this is from agriculture. But when we go to the next slide, we don't really see that. We see Visalia up here a little bit, but you see East LA in 2024 and East LA in 2016. So what this tells me is just how much of an effect those fires are having on total particles in the air, our black carbon, and you saw it through all three graphs where all three were higher for East LA. So some conclusions. So what I can draw from this is that black carbon is emitted at ground level and resides at low altitudes in the atmosphere, as we saw through our vertical profiles. Also, the LA Basin differences in average is expected, but the maximum values from 2010 to 2024 is concerningly higher, and if that's what's happening due to fires, then wildfires are a giant threat to our health. Also, hotspots tend to be similar in 2024 and 2016, definitely for the Central Valley, except for the San Bernardino area where we saw an increase from 2016 to 2024. And then what is the main source of black carbon in the Central Valley? So this is what I would like to do for future work. I would love to look into what is that main source of black carbon in the Central Valley. Just due to the fact that we didn't see that rise in ammonium, obviously we can't infer that from just one graph on one day. But it is interesting to see that we don't see that. What is the difference in black carbon production between prescribed burns and wildfires? So you know that prescribed burns are not cure, but are how we're going to prevent these wildfires. So it'd be interesting to see how this black carbon production differs between our prescribed burns and our wildfires. Now, so whenever I walked out of lectures or I read textbooks, at the end I would walk out and be like, oh my god, like the world's ending, like we need to hunker down. But I would like to assure you that black carbon is not that. Black carbon has about a lifetime, about 1 week in the atmosphere, like I said in the beginning of the presentation. So emissions could be reduced with more stringent policy. So with stricter legislation, we could cut down on our black carbon, not easily, but pretty quickly. And I show this picture not because I want us to go back into lockdown and have to go back to school online, but it does show you what less human activity does, and with more stringent policy, hopefully we could maybe make the LA Basin look like this. Finally, I'd like to acknowledge everybody on this slide for their continued support throughout this SARP program. I'm extremely grateful for this opportunity, and I'm happy to answer any questions. Tom.
On slide 14 with the Salton Sea and the, I believe, Central Valley, why is there such a much larger increase in black carbon for the Salton Sea compared to the Central Valley? I'm not sure.
Well, what I infer from it is that the Salton Sea and the LA Basin are relatively close together. So we could see something where like wind is bringing that black carbon, because obviously there's not a lot of people like, why would anyone want to live near the Salton Sea? But and then also, we did see, like, when we were flying over in 2024, we did see fires that were sort of going that way. So that could also be a reason why we see so much higher Salton Sea and so much higher black carbon near the Salton Sea. Done.
So we flew through, on the P3, we flew through some fire. Did they get measurements on this P2 back when we were in the fire, or?
I don't think when we were in the fire, but maybe above it. I'm honestly not sure. I have to refer back, but I'd love to look at it. Dan?
And actually, along those lines, can you go back to the slide that shows, you were just at it, I think, the flight from this year over the Central Valley?
Yeah.
Yeah, so on the leg, when we were headed northbound along the Sierras there was an active fire happening, but it looks like the readings are really low. Is that because the plane was too high, or did we miss the plume?
Yeah, it could be just we were too high. Yeah, I would assume that it's due to the height, and that's why we're not seeing those heavy black carbon readings in that area. Or something like wind or something like that, but I would have to look further into it in order to give you a further answer. Ben?
I was just curious, you talked a little bit about like more stringent policies being
Mhm.
a fix for those health effects. Are you aware of like any policies that we have today that limit black carbon, or is that not really something that's in our laws today?
Yeah, so you have like smog on cars, obviously, that limits our black carbon, but also you have, like I said, sort of those prescribed burns, which I think would be the biggest prevention of this wildfire. I mean, not this wildfire, of this black carbon. We saw how much these fires affect our black carbon, our levels. So I think that prescribed burns is probably the biggest policy that we have for our black carbon. But yeah, thanks for the question. Devin?
Why do we see a spike in black carbon around like 1,500 feet?
So like right around here probably?
Yeah.
Yeah, so as I Sarah stated, it's not that we necessarily see it at 1,500 feet. It's more that that's where like a majority of our readings are from 1,000 to 2,000 feet, given that's where the P3D was mostly at when I'm getting this data. But as it's emitted at ground level, it's safe to assume that it's not safe to assume that it's constant throughout the 0 to 2,000 feet, but that if we averaged it, that would be a representative of what is between that 0 and 2,000 feet. Josh?
The 1,500 to 2,000 feet area kind of interests me. I was wondering if you looked into the boundary layer at all.
I didn't really account for the boundary layer in this one, but given this drop off, I'm not going to assume, but given the drop off, I would assume that it's, which I think other presentations should go into further. Cool. Any other questions?
Is there any questions on
Garrett?
Jack?
Do you have a sense of why the hotspots for black carbon emission kind of moved east in the LA Basin?
I don't. It could be, we could have seen fire in that area. Where is that hotspots one? This one, right?
Yeah.
So what was interesting and what I originally wanted to sort of hone in on is, but I think it would have taken a little too long for this presentation, is there's this sort of, well, one, we do a missed approach here. So this is, I can't remember the airport, but what this, so Grand Terrace and Colton, there's like sort of mountain ranges, like almost like right here, and there's a highway that runs basically like this. So I should do this with a pointer instead of guarding your view. So there's two highways, I believe it's the 210 and the 67 that go bang and bang. So you're in between those valleys, and we could see it because of that, like where we see it getting trapped in that sort of valley between those mountains. But it wouldn't explain why we don't see it in 2016, because those highways are there in 2016. So it could be fire, but I couldn't give you a definitive answer.
I think Ben is on the right track. In 2016, we didn't get all the missed approaches that we got in 2024 in that region. Especially Ontario. One of the reasons that we decided to base out of Ontario is because we wanted to get some sampling low over Ontario. And so this is, and we also didn't get into the Long Beach airport as frequently in 24 as we did in 20. So part of what you're seeing is the sampling bias, but another thing that's changed a little bit over that time period is there's been an increase in the number of warehouses in the Ontario region, and we're seeing higher NO2 pollution in that region, which is from the diesel trucks, which is also producing the soot. And so one policy action you could take to reduce black carbon is to reduce the number of diesel vehicles in the basin. And it turns out that electric trucks would be a great solution for going from the port to the warehouse. It's a short distance and you can charge easily between those two locations.
Thank you, Barry.
Great presentation.
Thank you.